Sandeep, please unmute yourself.
Yes, sir.
So good morning, everyone.
Yes,
We
sir.
have this fifth consecutive day of the webinar series. And the speaker for today is Professor Rajendra Singh from IIT New Delhi, IIT Delhi. So he'll be speaking on electrical measurements of materials and devices. I request Dr. Sandeep Kumar to kindly introduce the speaker formally.
Thank you, Yashpal. Hello, everyone, and welcome to the today's webinar. And I am pleased to introduce today's speaker, Professor Rajendra Singh from Department of Physics, IIT Delhi. Professor Singh did his master's from DBS College, Dehradun in 1995. After that, he joined Inter-University Accelerator Center for PhD. His PhD work was related to the study of the effect of swift heavy ion radiation on electrical properties of silicon and gallium arsenide. After that, he joined Walter Schottky Institute, Germany, as a postdoctoral fellow. He worked on design, fabrication, and characterization of indium phosphide-based heterojunction bipolar transistors there. In January 2004, he joined the Max Planck Institute of Microstructure Physics, Halle, Germany, for his another postdoctoral assignment. There, he worked in the area of direct wafer bonding and layer splitting of semiconductors for the fabrication of silicon on insulator and strained silicon on insulators. There, he also initiated activities on hydrogen implantation-induced layer splitting of gallium nitride, aluminum nitride, and zinc oxide. He joined the Department of Physics, IIT Delhi in November 2006. His area of interest are gallium nitride-based materials and devices, gallium oxide-based devices, growth and characterization of semiconductor nanowires, 2D quantum materials and devices, MOCVD, and MB, growth of semiconductors and quantum materials, nanolithography, and nanofabrication. He has made significant contributions for the establishing of state-of-the-art nanoscale research facility at IIT Delhi. He has about 140 publications in international journals and a similar number of publications in national international conferences and workshops. He is the recipient of the MRSI Medal Award for 2017 and the Teaching Excellence Award from IIT Delhi in 2018. On a final note, he is also a fascinating individual, and we are grateful for his presence among us today. Without further ado, I would like Professor Singh for the talk.
Yeah. Hello. Yeah. Good morning, everyone.
Good morning, sir.
Yeah. You can hear me? Yashpal?
Yeah, sure.
Yes.
Okay. Sandeep, Dr. Sandeep
Yes.
Kumar, thanks. Thanks for the kind introduction. So let me first thank the organizers, Dr. Yashpal Singh and Dr. Sandeep Kumar, for initiating this webinar series on characterization of materials, which is going to be useful for many people, including the PhD students and postdocs. And I have actually made my presentation related to the electrical characterization of semiconductor materials and devices. So first, let me just try, because this is the first time I am giving a talk on Zoom. Mostly we are using Microsoft Teams. So let me just try to share my. Okay. 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 So I think I have to go back. Yes, sir. Okay. Okay. F5. Is it visible? The slides are visible to everyone?
Yes, sir.
Okay. And I am audible?
Yeah, it's fine.
Okay. So आप जा सकते हैं. Okay. So, a very good morning to everyone who is attending this webinar. So first, I would like to know that the participants, I assume that many of them are PhD students or master students and even postdocs also. Is it correct, Yashpal?
Right,
Yes,
sir.
sir.
It's correct.
Okay. So actually the presentation which I have made is keeping that kind of audience in mind. But for the details, like let us say for more advanced kind of measurements, or if you want to know a little bit more, then somebody can send me an email also and I can reply to that. And we can also later on tell them what kind of facilities are existing for electrical characterization. So recently, like let us say, we are going to establish a big electrical characterization lab at IIT Delhi as a central research facility. But that will be coming up in next 1 year or so. So it would be interesting actually. So number of different electrical characterizations can be done. So let me start actually. I think the top portion somehow I cannot see. Anyhow, so there is something which is appearing on the top which I want to avoid. Okay, so here is the outline of my talk. Uh, what I am going to show today is about the DC electrical characterization. You see, electrical characterization of materials, primarily the semiconductor materials and the devices. So it is actually depending upon the final application. So some devices are only like, let us say, DC type of devices and some others are also AC. So something like a transistor or even a switching diode. So here mostly what I'm going to tell you about the DC electrical characterization of the materials and the devices. And first what I will do is I will talk about the resistivity and Hall measurements of semiconductor thin films. And that is using the 4-probe technique, the famous, many of you might have heard about the 4-probe technique. And after that, what I will do is I will talk about the IV measurements. Again, the DC current voltage measurements on Schottky diodes and ohmic contacts, because it is very important whenever we are making any electrical measurement, suppose resistivity or Hall measurement on a semiconductor thin films, you need to have very good quality ohmic contact in order to get very reliable and good quality data. So I will talk about the ohmic contacts and what are the parameters by which we can characterize a ohmic contact. We can say this is a good ohmic contact or not. And then Schottky diodes. So the IV measurements of a Schottky diode, it's a device actually which is used in many applications. So used for photodetectors, it is used for switching diodes, high power switching diodes and mixers and so many applications. So what we will talk about is the very briefly, not like I said, going too much into the details, but what I will try to highlight is the important parameters of a Schottky diode, which we can actually measure using the current voltage technique or characterization. Then I will come to the capacitance voltage measurements. So here there is no DC current which is flowing. It is only what we are doing is we are applying a DC bias, DC voltage, and we are measuring the capacitance of a particular device. I have taken again Schottky diode as a reference, and what we can measure using this CV measurement or CV technique. And finally, I will just touch upon, if the time permits, about the CV measurement on a MOS capacitor, because this is actually just the beginning of a very important characterization of a very important device, what we call the CMOS transistors. So in the case of CMOS transistors, we measure IV curves, IV graphs. We also do CV measurements, and that is actually basically tells you the quality of the transistor, how you can use, whether it is usable even for high frequency application, which it is supposed to be or not. And the important parameters of the MOS capacitor, because MOS capacitor is at the heart of a MOSFET, what we call the MOS field effect transistor, metal oxide semiconductor field effect transistor. So before moving ahead, first what I would like to do is just introduce my group to the audience so that you can appreciate what kind of measurements and what kind of research we are doing at IIT Delhi. And if anyone needs some kind of, let us say, guidance or some discussion, they are always welcome to contact me. So in our group actually at IIT Delhi, mostly we are working on at present, first of the prime material is the wide band gap semiconductors. So as you see, we do the growth also and characterization. So in the characterization, we also do electrical characterization plus some other optical characterization, structural characterization on gallium nitride and related materials, and a new very important material, which is gallium oxide, which what we also call is the ultra wide band gap material. So we prepare the thin films, we prepare the nanowires, synthesize the material, and also fabricate the devices using our nanoscale research facility. So the kind of devices we fabricate is the electronic devices, optoelectronic devices, and so on. Then another very important theme in our research group here is the study of electrical transport properties of gallium oxide and gallium nitride based materials as well as devices. So this is the topic which, like, let us say I am talking about today. So we also fabricate Schottky diodes and high electron mobility transistors. So these are special category of transistors which are used for high power and high frequency application. Something like practical point of view, like 5G applications nowadays we are looking for. So these are the HEMTs, gallium nitride based HEMTs, which are the enabling devices for this technology. We do Hall resistivity, current voltage measurements, capacitance voltage measurements, and also a specialized kind of technique we use is what we call the low frequency noise, or also 1/f noise measurements. Although I'm not going to talk about this today, but this is also one kind of research we do in our group. So another thing is we also study the current voltage characteristics, the capacitance voltage characteristics of novel heterojunctions or heterostructures. Something nowadays which have come up is something like 2D materials. You might have heard about graphene or molybdenum disulfide or molybdenum ditelluride. So a class of 2D materials having like different kind of properties like metallic, semiconducting, insulating, and so on. So these 2D materials, if we reduce their thickness, then their nature of band gap and the amount of band gap changes. So this is a very fascinating property, and they obviously have quantum confinement in one direction. And how their heterojunctions with normal inorganic semiconductors, something like silicon or gallium arsenide or gallium nitride behave. So a few years back, one of my PhD students, he worked on graphene on GaN heterojunctions. And recently, one of my PhD students worked on MOS2 gallium nitride heterojunctions. So you can obviously see our publications, which we have done in the recent past on these topics. And as Dr. Sandeep Kumar also told, I am also from the PhD from the same institute. And one of my specialization is ion implantation and irradiation on semiconductors, materials and devices. And we also do the irradiation using gamma rays. So what is the effect of this irradiation, specifically gamma rays and ion irradiation on semiconductor material and then the devices? And then we try to establish a correlation between the effect which the material has seen and the effect which we are now observing in the devices. So it is not straightforward always to carry forward what we see in the materials, the effect we see in the materials, that it is clear or it is sufficient to explain the effect that we see in the devices. So we have to do a number of investigations and try to establish this correlation. And one of my recent PhD student who has submitted PhD, we have done a very good study on LGAN-GaN HEMTs, because you see these high electron mobility transistors, they are going to be used for defense applications, space applications, which are actually radiation environments. So we have explored this thing, and a few good publications we have done in this area. And this we have studied everything using the current voltage and capacitance voltage and resistivity, Hall. These are actually the measurements which we have done apart from other investigations. So then we are also carrying out, Dr. Yashpal Singh is also, let us say, one of our collaborators on studying the effect of irradiation on swift heavy ions on gallium oxide. There's a recent publication from his student, the effect of this ion irradiation on the gallium oxide devices. And then the MOS2. One of my PhD students is also working on the effect of gamma ray radiation on MOS2, because this is a very nascent field. Not many people have worked in this area. So now this is actually more or less, which shows you the research activity in my group. Now I go to the, okay. So I start with some basics. So you see the conductivity or the resistivity of materials. So if I roughly classify, what we have is, we have very low resistivity of the order of micron centimeter for metals. And then we have semiconductors. That's why we call them semiconductors. And after that, we have the insulators. So it's not that we have a very sharp boundary between the how much is the resistivity or conductivity of a metal and a semiconductor. Sometimes semiconductors, if you dope too much, they also show metallic kind of behavior. But what we know is the range actually, the range in which the resistivity of semiconductors fall, and what is the typical range of the resistivity of insulators. So what these measurements, the resistivity and Hall measurements, what I am going to describe in the coming slide, they are more actually with respect to the properties of normal semiconductors. Okay, not on the very high side, or not, let us say, the resistivity is not too much high or too much low. I will show you those ranges also with the appropriate graphs. So as you see, in a semiconductor, we have a conduction band, we have valence band. We also know that we have intrinsic semiconductors, which are pure semiconductors, although they don't exist that much. Like, it's very difficult to make a intrinsic semiconductor, but still close to that one. Then you have N-type semiconductor, and then you have P-type semiconductor. But if I assume that in a semiconductor, both electrons and holes, so these are free electrons in the conduction band and free holes in the valence band as charge carriers. So then what we have is the current density, which will be given by this relation sigma E. So this sigma, so this is the conductivity, which is given by Q, which is the elementary electronic charge, and multiplied by mu n. Mu n is the mobility of the electrons, n is the electron concentration in the semiconductor, plus mu p, where mu p is the mobility of the holes and p is the concentration of the holes. And this is the electric field. So I can use this expression to connect between the current density, which is flowing in a particular semiconductor. And current density is nothing but current divided by the area of cross section. And the conductivity is related to the resistivity as sigma is equal to 1 upon rho. Okay, so this is actually the relation between, so it's the reciprocal of resistivities. Conductivity is the reciprocal of resistivity. But in the semiconductors, the situation becomes little bit simpler, since we have law of mass action. What we have is the NP product is equal to Ni square. That I think most of you know. So what happens is that in an N-type semiconductor, what we have is N is very, very high, very, very large in comparison to the P. So in this relation, if you see, if N is maybe 10,000 times higher than P, so then this second factor you can neglect, because in the mobility, there is a difference. Mobility of holes is usually lower. There is a factor difference of a factor, or maybe maximum 10 times or something like that one. But in the N and P, in the same semiconductor, I'm talking about the same piece of semiconductor, you can have many orders of magnitude variation, depending upon what is the value of N. So we have to follow NP is equal to Ni square. Ni square is a fixed value for a particular semiconductor at a constant temperature. So now what I have is a more simplistic relation. Rho is equal to 1 upon Q mu n n for n-type semiconductor, or sigma is equal to Q mu n n. So it means the current which is flowing in a particular semiconductor, it is due to one particular type of carriers. These carriers we call as the majority carriers in semiconductors. The other type of carrier we call the minority carrier. So in the flow of DC current inside a semiconductor, the main role is played by the majority carriers. But it's not that the minority carriers are not important. In many applications or in many cases, they also play a very big role, specifically in the recombination phenomena. But I am not going to talk about the recombination. So what we have is, so resistivity or the conductivity, I use the relation Q mu n n. Mu n is the mobility of the carriers, of the free electrons. If it is a p-type semiconductor, then I will be having the relation sigma is equal to Q mu p e. I want to just tell you that what are all the different kinds of semiconductor samples that you may come across in a laboratory. People are working even with semiconductors, different types. You see different type of material and different type of crystalline structure of the material and different type of its form. Form means it can be a thin film, it can be a nanofilm, it can be a little bit thicker film, or it can be a substrate, and so on. So what I show you on the left-hand side is the bulk semiconductor substrate. So this is what we sometimes also call the wafer of a semiconductor, which is circular in shape, more or less. But the bulk semiconductor substrate means this is a self-standing substrate of a particular material. Suppose it is silicon. So then this is a complete silicon, a thick piece of silicon. And usually the thickness of these substrates is of the order of few hundreds of micron. Okay, even I can just show you the bulk substrate. Suppose silicon, in the market commercially you can procure, you can get very good quality silicon substrate, germanium substrate, gallium arsenide. These are direct band gap semiconductors, indium phosphide, silicon carbide, even gallium nitride also, and even oxides like zinc oxide. So you can get even single crystalline. What I have written is the form of the substrate or the crystalline nature of the substrate. So one thing is depending upon its thickness, physical thickness. So we call actually bulk semiconductor substrate. If it is freestanding, it is not actually deposited or in contact with some other material as such. So it can be a single crystalline. All these materials available in single crystalline: zinc oxide, tin oxide, copper oxide, gallium oxide. So many oxide materials, and most of the oxides, many of the oxides are also semiconductor materials. But there are some things like, let us say, difficulties, something like in zinc oxide, p-type is not available. So that's why they are not so popular as far as the electronic or optoelectronic device application is concerned. But otherwise, they are also semiconductors, many of them. And now there is a polycrystalline. So this bulk semiconductor substrate could be polycrystalline also. Okay, so that is also possible. You can have silicon polycrystalline wafer, germanium, everything. So that is also possible. So this is one type of substrate. Second thing is, now you see on the right hand side, there is a substrate. And on top of that, I grow a semiconductor thin film. It can be the same material or it can be different material. If it is a different material and it is a single crystalline grown over a single crystalline substrate, we call it a heteroepitaxy. If it is the same material, then it is called the homoepitaxy. But it's not necessary. It can be an amorphous substrate. On top of that, you grow a polycrystalline semiconductor film. Something, suppose on glass you deposit a zinc oxide thin film, is going to be a polycrystalline. So different kind of now combinations are possible. So you see, so a thin film, usually from the thickness point of view, we usually explore or study the thicknesses from a few nanometer to about micrometer. Okay, if it goes beyond micrometer, really, then it becomes actually, its properties resemble more and more to the bulk property. A few nanometers, a few hundreds of nanometer, and all those ranges, still we are in the thin film regime. And again, now you see thin film can be of these materials and single crystalline, polycrystalline, and even amorphous also. Okay, so like gallium oxide, if you deposit over sapphire, by spin coating method, then it is going to be amorphous. Or if you then anneal it, then some small grains will start nucleating in this thin film. It will become a kind of nanocrystalline. So all these possibilities then open up. And in the case of thin film, if I am trying to explore the electrical properties only of the thin film, I am using substrate just as a mechanical support and to grow a thin film. Then what I would like to have is this substrate which should be insulating, so that from the top, when I am exploring the electrical properties of the thin film, so I get only the contribution from the thin film. So now is actually the technique which we are usually using in the characterization. So I come to now the two important electrical measurements. One is the resistivity of the semiconductor material or thin films, and second thing is the Hall effect. So resistivity in our lab. So you see, many people, many of you might be experimentalists and you are working in the lab. So sometimes, depending upon the facilities that you have, you do two probe measurement, and using the two probe measurement, you calculate the resistance of your thin film or substrate, and then using the physical dimensions of the substrate, or the thin film, you get the resistivity. But there is a lot of error actually in that resistivity measurement. That is going to happen in a semiconductor. That kind of measurement gives you a huge error. So that's why the technique which is used, which is more reliable and more accurate, is the 4-probe method. So a very simple 4-probe method is what we call the collinear 4-probe method. So what you see here is these figures I have taken from the famous Physics of Semiconductor Devices book, SMZ. So what we have is that there is a substrate or a thin film. It can be thin film. So W is showing here the thickness of the thin film or the substrate. So I don't distinguish now between a bulk substrate or a thin film. I have already described that. Okay, so this is the material or the sample I'm going to explore. Its physical dimensions A and D, and I don't need to elaborate it. Mostly in our lab, we use 1 by 1 centimeter square sample, or smaller or a little bit bigger. It's not that most of us are studying 2-inch wafer or 4-inch wafer. That is usually doesn't happen in the research labs, unless and until there is some pressing application. Okay, so then this is a small piece, maybe 1 centimeter. And these are the 4 probes. So these are actually some metallic pins, and they touch 4 points on the sample substrate. And the gap between these 2 probes is, let us say, capital S, which is shown here. So the current actually, the DC current given by a DC current source. So you can use a Keithley DC current source for it, which is a very precise current source. So the current flows through the outer 2 probes. And the voltage that you measure between the inner 2 probes. So in this way, what you can do is you can remove the error which is coming due to the contact resistance. So in this case, you remove the contact resistance and you get the resistance only coming from the material, from the sample. So what happens in semiconductors is, even other materials also, that when you make a contact between, and this I am going to describe later on in little bit more detail, you make a metal semiconductor contact, there is always a barrier which is formed. And this barrier actually, if it is too high, then it causes a huge contact resistance. And this, when you measure actually, when you are measuring the voltage, then this contact resistance also comes into play using 2-probe method. But in the 4-probe method, we can try to remove it as much as possible. So this is actually what the presumption, A and D, the dimensions of the sample are much larger than the thickness. So in thin film, always it is true, even in substrates also. If you have 1 centimeter sample, then the thickness typically is a few hundreds of micron. In thin film, it is less than 1 micron. So this condition is always mostly fulfilled. So the sheet resistance is a very important parameter as far as a thin film is concerned. We call V by I. Okay, the current which you are flowing through the external 2 probes or outer 2 probes, and the voltage which you are measuring across the 2 internal probes, V by I, this is actually the nothing but the sheet resistance. And there is a correction factor also, which I have written here. There is a correction factor. I will show it graphically. So the unit is omega per square. Okay, per square, this is not a physical dimension. This is actually the convention, omega. The unit, the dimension of sheet resistance is that of a resistance, that is ohm. So resistivity, rho is equal to now. So if I want to calculate what is the resistivity, so you see experimentally I have measured the sheet resistance. And if you already know the thickness, W, here I'm taking W as the thickness of the sample. So this thickness of the sample you have to know. If you don't know it, then you cannot calculate the resistivity. Okay. So before doing your measurement, you should know the thickness of the sample. So R square or sheet resistance multiplied by thickness gives you the resistivity. O in ohm centimeter. You can, this is actually ohm centimeter is the conventional unit of resistivity. SI unit will be like, let's say, ohm meter, but you can always convert them into each other. Okay, so this is now how we have measured the resistivity using the collinear 4-probe method. You see here, there is actually a disc also, which is shown. Here also we can do. And you see D is the diameter. But this is something like, let us say, I have taken from the book itself, SMZ. But in most of the cases, if you are experimentalists, you will understand it is very, very difficult for a brittle material or a crystalline material like silicon, germanium, gallium arsenide, any other sapphire to make it in a circular shape. And it is not required actually. So this kind of geometry as such is not so popular. It's just shown for actually that you can do that. But most of the samples what we have are either square sample, rectangular samples, or irregular shaped samples. So this is actually the correction factor. Okay, so correction factor is this D, the dimension of the sample, divided by the gap. Okay, the S between the, or the distance between the two probes. And on the y-axis has been shown the correction factor. So you can see that and this is shown for different A by D. So mostly in our cases, A by D is 1 or 1/2 or something like that one. So more or less the graph is the same. Circular I am actually just neglecting. So you can see this is the kind of thing. This is the kind of graph as far as the correction factor. So you see if you are having almost 10 or above, then the correction factor is something like, let us say 4.3 or 4.4. So you have to introduce that 4.4 correction factor. Otherwise, if you don't introduce that, then you already see that there is going to be a huge error in your sheet resistance and then eventually the resistivity calculation. So this graph is very useful. You have to use this graph for calculating the correction factor. So this is actually what I am depicting, and which is what I told you earlier, that you see the resistivity. So here, so this is actually, it's not that this is just a theoretical graph. This is an experimental graph taken from SMZ's book for silicon at 300 Kelvin. And the same formula, rho is equal to 1/q mu n. So what you see here is the resistivity of semiconductors. It spans many orders of magnitude for the same sample, same silicon, you see, by doping. So one end you have 10 to the power minus 4 ohm centimeter, which is more towards the resistivity of semi-metals. And then on the other side, you have 10 to the power 3 ohm centimeter, which is going more towards the insulators. Okay, so they can span actually almost 7 or 8 orders of magnitude. And this is actually the reason why semiconductors are so useful for making different types of devices. So we can modulate the resistivity of these materials by many orders of magnitude, which is not possible in insulators and conductors like metals. So corresponding impurity concentration or dopant concentration, you can see how much they vary, 10 to the power 13 per centimeter cube and up to 10 to the power 21. So if you have heard the terminology, the degenerate and non-degenerate semiconductors. Okay, so usually what we have is when we are having nominal kind of doping in semiconductors, 10 to the power 14, 15 per centimeter cube, 16, 17, and so on, we call them little bit like, let us say, nominally doped semiconductor. And in that case, they are called the non-degenerate semiconductor. Now beyond almost 10 to, it depends upon the semiconductor, but typically 10 to the power 19 and above, they become degenerate semiconductors, and their properties start more something like a metallic nature. They don't show too much of semiconducting behavior. So you can see corresponding to, let us say, 10 to the power minus 3, the doping concentration. So this is both for p-type as well as n-type. So the graphs have been like, let us say, 2 graphs are there because the mobility of p-type or the holes is less. So that's why the resistivity is higher. So at 10 to the power minus 3, what you have is 10 to the power 20. So usually in most of the semiconductor devices, normal devices, you don't dope up to 10 to the power 20. It is for some specific application that you have to do some region of a semiconductor device for 10 to the power 20. Typically, we are in 10 to the power 18 or below, or like this one. Another important point which you can see, actually, whenever we see a graph in a book, and standard textbook like SMZ, from the same graph, actually, you can extract a lot of information. And that is what should be our aim, actually. As PhD students and postdocs and scientists, we should try to extract a lot of information which is actually already embedded inside that graph. So another important thing which you can see is, you see 10 to the power 13 per centimeter cube. But what is the intrinsic carrier concentration of silicon at 300 Kelvin? 1.5 10 to the power 10 per centimeter cube. What it means, if you don't dope silicon, it is pure crystal. At room temperature, the carrier concentration should be 1.5 10 to the power 10, which is very, very low. But you see, experimentally, it is not possible to get 10 to the power 10. And it's very even difficult to measure also. But at the first place, it is not experimentally possible. That kind of pure silicon crystal is not available. So whatever is available is something of the range of 10 to the power 13. So almost 1,000 times higher. So you see, to get a very, very pure semiconductor crystal whose conductivity or whose carrier concentration is close to intrinsic carrier concentration is very, very difficult to obtain, specifically with example to silicon. So now I come to the other measurement, which we call the Hall. The Hall effect, I think most of you know, that you take a sample and then across the two ends, you pass a current, and then in a perpendicular direction, suppose here in the Z direction, you have applied a magnetic field, a DC magnetic field. This is the DC electric current which is flowing. And then what will happen is, due to this, there will be a electric field or the voltage which will be developed across the Y direction. This is what is the Hall effect. And the Lorentz force you already know. There is a Lorentz force between this is Lorentz force faced by these carriers. In the case of semiconductors, what happens is, you see, if this slab which I am showing here, it is p-type, and this is the battery due to which the current is flowing in this direction. So if I have added this positive terminal to this end, then the current will always flow like this one, whether it is a p-type semiconductor, n-type semiconductor. But in this case, what you will see is holes are flowing actually. Holes are the current carriers here. The current is flowing due to the holes. So the holes are going in this direction, in the negative x direction. And they are feeling a force, downward force, Lorentz force, which is actually in the negative y direction. So due to this, what will happen is the holes will accumulate on the lower face of this slab. So you will be having actually an electric field which will be generated or which will be created in the positive y direction. So now you see the Lorentz force pushes the holes towards the negative y direction, and this EY, this electric field, what we also call the Hall field, this pushes it towards the upward direction, towards the upward face. So there will be eventually a balance of the two forces. So this will be given by Q EY is equal to Q Vx Bz. What is Vx here? Vx is nothing but the drift velocity of the holes. So this drift velocity is, if you remember the relation, the drift velocity is proportional to the electric field. So this proportionality constant is called the mobility of the carriers. So Vx is equal to mu Ex. Okay. So this is the electric field which is being applied using the external voltage source to the across the slab. So now we have actually these equations in front of us, and what we can do is we can actually So this is the relation Jx is equal to QVxP, where is the carrier concentration. This is the drift velocity. Drift velocity is mu e. So this complete relation is nothing but Jx sigma is equal to sigma e. Okay, this is the same relation. I have just rearranged the terms so that Vx appears as the drift velocity. So the Hall voltage can be now represented by this relation. Okay, so just let me. Actually, I just wanted to hide these things because they are okay. Now it's better. So Hall voltage is given as E y and the thickness of this sample. So this is actually the Hall voltage, and this EY you can write from these terms. Okay, EY is equal to Vx Bz, and Vx you can write from this equation. So it comes out to be Jx Bz W by Qp, and this relation usually is written as Vh is equal to Rh Jx Bz W. Jx Bz W. So these three terms actually we already know. I know what is the magnetic field I have applied. I also know what is the thickness of the sample. And the third thing is I know what is the current which is flowing to the sample, because I know the geometrical dimensions and I know the voltage. So this RH factor actually is not known, or what is 1 by QP. So you see here, this is related to VH. VH is equal to RH JX BZW. So VH experimentally I am measuring. And this is what is the Hall effect study. I am experimentally measuring the Hall voltage. So I have measured the Hall voltage, other three things I know, so I can calculate the factor RH. So once I have calculated the RH, this is called the Hall coefficient. So this Hall coefficient is equal to 1 upon QP for p-type semiconductor, and it is equal to 1 upon minus 1 upon Qn. You can see also in the case of electrons also they will go in this direction. So depending upon the polarity, so I can tell that this is a negative or this is positive. So in the case of n-type semiconductor, I have the relation RH is equal to minus 1 upon Qn. So you see, I can calculate Q is the elementary electronic charge. So P I can calculate means in the p-type semiconductor, I can calculate the hole concentration, and I can also calculate the electron concentration if it is an n-type semiconductor. So using Hall effect measurement, what I have done now is that I could calculate the carrier concentration in a semiconductor. So you see, this small RH factor, I will just tell you briefly, but before that, so in a semiconductor sample, in a material, the two important things to be known, as I have shown you also depicted to you, two very important things to be known are, first thing is the resistivity, second thing is the mobility. But mobility, how I calculate? Okay, I don't have a direct technique to measure mobility here. So what we do is, we calculate the resistivity, then we calculate the carrier concentration by Hall effect measurements, and I know the relation sigma is equal to Q mu and N. So I have calculated N, I have calculated sigma, experimentally I have measured. So from this relation, I can also now calculate the mobility of the carriers. So using the Hall effect measurement, we can calculate the carrier concentration. So you have to do it in conjunction with the resistivity measurement. So once you do it in conjunction with the resistivity measurement, you can calculate three things now about the semiconductor material. You can calculate or experimentally measure the resistivity, the carrier concentration, and the carrier mobility. So that's why this electrical measurement, the Hall effect measurement and the resistivity measurement are actually the fundamental measurements as such in any semiconductor lab. Very, very important. Without that, you don't know anything about the electrical properties of the semiconductors that you are trying to explore. So just briefly, so that not to have error in the electron concentration, so actually it is given by small RH by QP and small RH by QN. So here actually these RH are kind of correction factors. So RH value you can just see here is 3 pi by 8 or is equal to 1.18 in the semiconductor where phonon scattering is the dominant scattering mechanism. So if you know that in this particular semiconductor, the phonon scattering is going to be the dominant scattering process, carrier scattering process, then you have to use RH of 1.18. So you see there is 18% error if you don't use it. In case it is a impurity scattering, ionized impurity scattering, then this is the relation, 1.93. So almost 2 times error is there in the calculation of the carrier concentration and eventually, let us say, the mobility also. So this important factor has to be kept in mind. So now you see this block which I showed a kind of from the book, we don't have in practical conditions, we don't have this kind of sample. We never have this kind of geometry. The kind of geometry we have is what we call is one of those geometries is the Hall bar geometry. So this is actually this Hall bar geometry, but for this Hall bar geometry, what you need to have is lithography and etching facilities, and which becomes actually sometimes a limiting factor. It's not so easy to make these kind of, if those people who work in semiconductor fabrication, they know that in any single crystalline material or even polycrystalline, making this kind of Hall bar geometry is not so simple. So we usually use the optical lithography and then the reactive ion etching to create this kind of Hall bar structure. So in this case, what you are seeing is that between 5 and 6, so this is a thin film which you have patterned actually and etched out in this way. So you have etched it out in this way. So you have the material left only here. Below is the substrate. There is no semiconductor material here. So what you have is there is a ohmic contact 5 and 6. You flow the current along this direction. So you see it is a perfect geometry. And now 1 and 2, you measure actually the longitudinal voltage from where you can calculate the resistivity, and across 2 and 4, you measure the Hall voltage. And these 2 and 4 or 1 and 3, they are perfectly symmetric. There should not be any difference between these 2 and 4. These should be exactly the same. The dimensions and their distance from this 5 should be the same. And that is exactly possible by optical lithography. So they should be perfectly symmetric. Then the Hall voltage which you measure is actually the accurate measurement, the very reliable and accurate measurement. So here I'm showing at the bottom, I'm showing this is actually a Hall bar geometry which has been fabricated on a particular semiconductor material. You can see the typical dimensions like 280 microns. So these are the contact pads using which you will make a contact with the wire, or maybe the bonding with the wire bonding you will do. And then this the circular portion, the dotted circular portion which is shown here, this is actually the semiconductor material which has been etched out. So this blue portion you see, this is the Hall bar geometry, and these yellowish things are what are being represented as the contact pads, metallic contact pads, and the dimensions you can see here. So this is the width, W2 is 5 micron and 100 micron gap, 60 micron gap. So all these things are possible if you have photolithography and etching technique available in your, like, let us say, fabrication facility. So this is actually a Hall bar geometry. Using this, if you have access to it, then you can do a very reliable and accurate measurement. But many of us know that this kind of thing is not available to all. So what we do is we have different kinds of geometries. There are other, we are called geometry for Hall effect measurements. So all these kind of geometries are possible, and it's in many cases actually, so it becomes difficult. So what we do is we take this arbitrary shape sample. Okay, this is called the arbitrary shape sample. So not necessarily like this one, it can be like, let us say, a rectangular, irregular piece also, a little bit at the corner there is a cut. All those things are taken care of. And in this measurement, what you do is, this is also called the Van der Pol technique. So it's also a 4-probe method, but you don't need to have collinear 4-probe. So what we do here is, we pass the current through these 1 and 2, you measure the voltage across 3 and 4. This is V43 by I2 is called the RA. RB is, you now switch actually, you change the connections. Between 2 and 4, 3, you send the current using a current source, you measure the voltage across 1 and 4. So RB is V1 by 4, V14 divided by I23. And now what you do is, RS, the sheet resistance now is given by pi ln2, the natural log, RA plus RB by 2. So using this relation, you can calculate the sheet resistance. And thickness of the sample multiplied by the sheet resistance gives you the resistivity. So this is actually many of you use this technique actually for the resistivity measurement. So this is the Van der Pol 4-probe method for resistivity measurement. In the case of Van der Pol Hall measurement, what you have to do is you have to send the current across 1 and 3 diagonally opposite contacts. So remember, it has to be perfectly symmetric. Then only, let us say, this kind of measurement you should do. Or otherwise, if you are not, you don't have a perfectly symmetric sample, then you have to take care of the voltages, which voltage you are measuring, and then you have to measure the exact value of the VH, or you have to know what is the exact value of VH. So if I assume it is a perfectly symmetric, then IN3, and then between 2 and 4, whatever is the voltage developed when I apply a magnetic field. So if I don't apply a magnetic field, it is a perfectly symmetric square sample, contacts are symmetrically placed, then there will be no VH generated. VH is equal to 0 if there is B is equal to 0. If there is B, then there will be a finite VH. Once I know the VH is the same Hall effect measurement, NS is equal to, which is the sheet carrier concentration, IB is the current, B is the magnetic field, Q, VH. And using this NS, if I know the thickness, NS by W, the thickness, it gives me the carrier concentration, volume carrier concentration. And from now again the same relation, the rho is equal to 1 upon Q mu N, because rho I have calculated from resistivity method. And now I calculate carrier concentration from the Hall method. So I can calculate the mobility of the carrier. So these three things we can also calculate from Van der Pol technique. The advantage of Van der Pol technique is that you don't need photolithography, you don't need reactive ion etching. So even if you don't have those techniques, this is a very, very reliable method for calculating the electrical properties of the material. So very briefly, I show you, many of you might have seen this kind of graph. So it's not that I can do this measurement, resistivity measurement at room temperature. I can also do temperature dependent, as I have shown you in my, like, let us say, group page also, or the group expertise, that we can do these measurements as a function of temperature. What extra you get? What is the extra information you get? So this graph actually depicts that thing. It's a very standard relation in semiconductors. Pn product is equal to Ni square is equal to Nc Nv, where Nc is the effective density of states in the conduction band, Nv is the effective density of states in the valence band, exponential minus Eg by Kt, which is the band gap of the semiconductor. So this is the kind of relationship which is followed by a semiconductor. So if I do Hall effect measurement, where suppose for N-type semiconductor, silicon example is taken here, 10 to the power 15 per centimeter cube. What you see here is over the entire temperature range, you see from 50 Kelvin, you don't need a very liquid helium kind of cryostat, but still, like let us say, if it goes up to 50, that's better. It's not 4 Kelvin or something is required. So 50 Kelvin to, let us say, higher temperature. If you do this, you see the variation of electron density or carrier concentration as a function of temperature. On the bottom axis, x-axis, you plot 1000 by T, the reciprocal of temperature. And then on the top axis, you can see the corresponding temperature in Kelvin. So you see, there are clear-cut 3 regimes. Okay, one what we call the freeze-out regime. Another one is the saturation range. Third thing is the intrinsic range. So you see, if you do this measurement, from this measurement, you can find out this graph, as I was saying earlier. You can find out a lot of information. So one thing, if it is in the intrinsic range, so its slope is very high. And the slope, as you see from here, you see this is actually Eg, Eg by K. So this is minus Eg by K. This slope is minus Eg by 2K, because I am plotting actually Ni, not Ni square. So it will be minus Eg by 2K. So K is Boltzmann constant. So basically slope is related to the Eg. So this is the electrical method for the measurement of the band gap of a semiconductor. So many of you measure the band gap of a semiconductor by different methods, by UV-vis spectroscopy or UV-vis absorption measurements. Some of you measure by maybe photoluminescence, but photoluminescence cannot be done on silicon or indirect band gap. So if you have an indirect band gap semiconductor, you want to calculate its band gap, then you have to do temperature dependent Hall measurements and then from plotting this kind of graph, and by fitting, you can calculate the band gap of a semiconductor. This is a very universal graph for all the semiconductors. The second thing which you can find out is the saturation regime. So saturation regime is the doping concentration. So from the saturation range, what you can tell is what is the carrier concentration. Okay. Then the freeze out range. So this slope actually, in this slope, what is happening is the carriers which are given by the donors. So first they are frozen, they are captured by the donors, but as the temperature is increasing, I am going towards this direction, towards the left, then what is happening is more and more carriers, more and more electrons are being donated by the donors, and then your carrier concentration increases. Eventually, when all the donors have been ionized or they have given their electron to the conduction band. So if I fit this freeze out range, its slope gives me the ionization energy of the donors. So you see, if I want to calculate the ionization energy of the donors, I can do again this temperature dependent Hall effect measurement. So you see, using resistivity, Hall effect, and temperature dependent Hall effect measurement for a particular semiconductor, I could calculate resistivity, I could calculate carrier concentration, the mobility, its band gap, its ionization energy, and so on. So now I come to the topic of ohmic. Dr. Yashpal, can you hear me? Hello?
Yes, sir, I can hear you, sir.
Yeah, so how much time I have? Because I have many more slides to go. So accordingly, I will actually arrange the talk now.
Okay.
How many more minutes?
Just a moment, sir. You can probably take 15 more minutes. 15,
Okay.
20. Yeah.
Okay, thank you. So now you see, I was from the beginning telling you the importance of ohmic contacts to semiconductor. First, what is an ohmic contact? So it is a metal semiconductor contact which has a negligible resistance, okay, relative to the total resistance of the material or device. So second important thing is its IV characteristic should be linear and symmetric. Okay. Ideally, for an ohmic contact, if you make two ohmic contacts on a semiconductor material and you do IV characterization, it should be linear and symmetric. Then it is a good ohmic contact. But that's not all actually. So it should have some physical properties like good adhesion also, and thermal stability for the device operation. And it should also have a very small contact resistance. But now actually I was talking to you earlier about, and all of like even in this 4-probe method, with the reference to 4-probe method, I was telling contact resistance should be small. Contact resistance should be small. But what is contact resistance? How can you measure experimentally or not? I'm interested to calculate even the contact resistance. So this is actually the figure of merit. So first I just show you, there's an important figure of merit for ohmic contact, what we call, remember this thing, specific contact resistance, R-C. So this is actually a figure of merit for telling whether this ohmic contact is good or not so good. Okay, what it is actually, it is the reciprocal of del J by del V at V is equal to 0. Okay, the current density when you do the IV measurements, so J as a function of V, and you take the slope, and its reciprocal is actually the contact resistance. Its units are omega centimeter square. Okay, so this is actually the important figure of merit to quantify a contact resistance. Whether contact resistance is low or high, using this figure of merit, this parameter, I can quantify that. And typically, another thing which I can give you is that for a good ohmic contact, the value of specific contact resistance should be in the range of 10 to the power minus 1 to 10 to the power minus 6 ohm centimeter square. So now you might be knowing that many of you, so you see you have deposited a thin film of zinc oxide on glass, and then taking silver paste, you do some measurements, and then you do some calculation, and you tell this is the resistivity, this is the carrier concentration, and so on. But there is a lot of error you have to remember there. There is a lot of error because you have not quantified actually. You might not have seen, even if you have seen it is linear and symmetric, but you have not seen how much is the contact resistance. So if you fabricate a device on this kind of material, using again silver paste, which you assume this is or indium contact, you assume it is good, but it is okay, but not very accurate. For very accurate measurements on any semiconductor material, on devices, it is of utmost importance to fabricate a very high quality ohmic contact. Without ohmic contact, the reliability on the measurements is not that much high. So I have already given you the number. If you have 10 to the power minus 1, it is okay. If it is 10 to the power minus 6, this is the kind of best what we get. So anything between 10 to the power minus 1, 2 or minus 3, it is, I think, more or less okay. Not the best, but still good enough to do some reliable measurements. So here I am showing you actually a graph which summarizes this thing, how to fabricate a good ohmic contact. Okay. And you can see what are the important things. So whenever you are depositing a metal, basically for creation of or fabrication of a metal semiconductor contact, you are depositing a metal over a semiconductor, and now you do the IV measurements. So what we calculate of this contact, there is a barrier which is formed, and this barrier is quantified by barrier height, what we call the 5BN, the Schottky barrier height. So in this graph, what I have shown you, I've taken from this Marius Grundmann's book. So contact resistance, you see the variation 10 to the minus 6 to plus 10 to the power 6. So this plus 4 and plus 2 are that actually not ohmic contacts properly. And on the y-axis, the square root of the reciprocal of the square root of donor concentration, 1 upon square root of ND. And on the top axis, what you see here is that the carrier concentration or the donor concentration in the material. So you can see it is increasing from like lower side to the 10 to the power 20 or so. So what important thing here is, I'm just summarizing it quickly, that if theoretically, so from the theoretical current transport behavior in metal semiconductor contacts, what you get is RC dash is equal to this one. Here you see this is a constant. This is the effective Richardson's coefficient, temperature. Only variable here is barrier height. So you see, if you reduce the barrier height, then the contact resistance actually, you see, it decreases drastically. So it is exponentially dependent actually. So you see, if you have a barrier height of 0.85 and 0.4, there is a 10 to the power 4 to 10 to the power 8 orders of magnitude decrease. So in this regime of current transport, you have to reduce the barrier height between the metal and semiconductor. There is another regime if you have a high doping. So this is this regime which I was showing you. Now there is another regime where RC dash is proportional to minus Q 5BN by E double naught, where E double naught is actually a tunneling parameter which is dependent upon the donor concentration. Higher is the donor concentration, higher it is. So if it is higher, then this is lower, it means this is higher, contact resistance. So what you have to have is, if you have higher donor concentration, so you can see the higher donor concentration is in this side. So if you have higher donor concentration, so then you can see the value of this one is higher. So eventually the RC dash value is going to decrease drastically. You see, this is the log scale. So you can see you can go from 10 to the power 0 or means 1 to even 10 to the power minus 6 by changing the dopant concentration from 10 to the power 19 to 10 to the power 20. So there are two ways to create very good ohmic contacts. One thing is reduce the barrier height, very low barrier height. Second thing is do the doping in the near surface region very high. Have a high doping concentration so that the metal semiconductor region is actually kind of tunneling. There is a tunneling which happens, and the electrons which are flowing, they don't see the barriers. So I just now maybe more or less, because I think I initially started that I'm going to tell you about a lot of other things, but maybe this will be the last thing which I'm going to tell you, that the transmission line model. So this is actually now, you see, I have told you this RC dash. It is a very important thing, figure of merit, but experimentally how to measure it. That's also important. So to measure experimentally, what we see is, I show you this kind of diagram. So you see, this is a R semi, this is a semiconductor. I have two metal contacts on it. Okay, if there's a 4 probe, then there will be 4, but I just start with the 2 probe measurement. This is called the transmission line model, okay, TLM method for the calculation of RC dash, the specific contact resistance or even the contact resistance also. So Then there is a contact resistance RC between the metal and semiconductor on both the side. I assume them symmetric. There is a resistance which is coming from the metal also. So the total resistance between these 2 points, okay, the resistance between these 2 points, which I am measuring using this 2-probe method, will come out to be 2Rm plus 2Rc plus R semi. I am actually interested only calculating R semi. I am not interested in this one, but somehow they are there. But usually Rm, the metal conductivity is very, very high. Its order of magnitude is very high in comparison to semiconductors. So that can be neglected. Okay, the resistance which is coming from metal, unless and until it is a very small contact, it is negligible. So I neglect that. So what I get is 2Rc plus R semi. RC is much larger than Rm. So now what I do is, in the TLM model, what we do is, we take the semiconductor sample. So this is the top view. Bottom is the cross-sectional view. And in the top, I am giving you the top view of the material. So we create actually these ohmic contacts, stripes of these ohmic contacts having width W. Here W is the width and the length L. So they are same actually, WL, WL. But the gap between these successive contacts is increasing. These are ohmic contacts, which I want to fabricate on my sample. Gap is D1, D2, D3, it keeps on increasing. So in the cross section, I'm showing you, this is the RC, this is the R semi, and this is the RC. So R2 RC plus R semi. Now what I do is, I take this equation. Okay, so this is RT is equal to 2RC plus R semi, as I have told you. Okay, is equal to R sheet D by W. W is the width of the this ohmic contact. Okay, and R sheet is the sheet resistance. So you know what is sheet resistance. This is resistivity divided by the thickness of the sample. Now what I do is, I plot actually. Okay, I plot total resistance, which experimentally I am measuring. I am passing the DC current, I am measuring the voltage across these 2 probes. So that is what I am measuring, RT. And these D1, D2, D3, D4. So successively I measure the RT between first 2 contacts, second and third contact, third and fourth contact, fourth and fifth contact, having gaps D1, D2, D3, D4, D5. Okay, and this is the equation in front of me. Okay, something happened. Yeah, so from the slope, now you see, I get this kind of graph and I fit it, linear fitting. From the slope is R sheet by W, as you are seeing. R sheet by W is the slope of this graph, and it is equal to R sheet by W. So from here, from the slope, W I already know because I have fabricated the ohmic contact. So I can calculate from slope experimentally, which I have measured. I can calculate the sheet resistance if I know the thickness. So here I'm using small t for thickness because W I have already used. So R sheet, thickness I know, I can calculate the resistivity. So even from TLM method, you can also calculate the resistivity of the sample. But that's not actually the main aim of this method. Specific, so what I do is, I have an intercept on the y-axis. So this intercept you can see from this equation is nothing but 2RC. So you see this intercept gives me the value of contact resistance. It will tell you how much is the contact resistance. And how much is the specific contact resistance? It is given by RCWL. W is the width, L is the length of the ohmic contact. So in this way, I can calculate from TLM model the specific contact resistance of a ohmic contact. So it's a very powerful method, very important method. And if you want to quantify the quality, then you have to see the linearity, the symmetric nature, and the specific contact resistance. So just briefly, actually, not now, I will skip 1 or 2 things, but since I promised, so what I will do is, I will just show you the Schottky contact. Ohmic contact I have already talked about. So you see, this is the energy band diagram of a Schottky contact. So Dr. Yashpal, I will take maybe another 10 minutes and then I will finish. Okay. Dr. Yashpal, can you hear me?
Yeah, so yeah, okay. Please, sir. Yeah, please go ahead.
So this is the energy band diagram. At the bottom, I have shown of a Schottky contact. So there is a barrier actually, which is formed between the metal. And this barrier is phi bn. So this is what we call the barrier height. And there are various models actually and various current transport mechanisms in a Schottky diode. I will not elaborate those, but what I will show you in the case of ideal diode, this is the kind of equation which holds true. I is equal to Is exponential QE by KT minus 1. Here Is is the saturation current density, reverse saturation current density given by A star. A is the area of the contact, A star is the effective Richardson coefficient, T square actually is the temperature, exponential minus Q phi B by KT. So from Is I can calculate actually, because other things are known to me, temperature and A star. So phi B can be calculated. So the two important parameters of a Schottky diode are the barrier height, the Schottky barrier height. Another thing is the ideality factor. So this is for an ideal diode, but for a practical diode, I do a little bit of change to fit the IV experimentally obtained IV characteristics. So this is Is exponential QE by NKT. N is the ideality factor. So for good diodes, usually you will get ideality factor below 2. So what ideality factor shows is, as I have depicted in this PPT slide also, it shows you the current transport, the relative dominance of different current transport processes in a Schottky barrier diode. Ideal case, harmonic emission, the value is going to be 1. It can be more than 1, which indicates that other current transport mechanisms like quantum mechanical tunneling, recombination are also into play. So I now want to calculate experimentally. I want to calculate what is phi b and what is n. So this equation, a kind of simple equation is front of you. This is what I am going to use. So this is actually the models for theoretically explaining the barrier height in a Schottky barrier diode. The Schottky Mott model, phi m minus chi. Phi m is the metal work function. Chi s is the electron affinity of the semiconductor. And then the Bardeen model, two extreme models actually. Eg minus phi naught, where phi naught, Eg is the band gap, phi naught is the charge neutrality level. I don't go into the detail, but Schottky Mott model is for the ideal case, and Bardeen Mott model is sort of, let us say, diode which is not so good. And mostly what we obtain is the diode which is having a barrier height in between these, but predicted by these two models. So I'm just using the kind of reference of my PhD student's work, Dr. Ashutosh Kumar. So you see, I'm just showing you one example. There is a gallium nitride film on sapphire. We have done complete Hall measurements, resistivity measurements on it. On the sides, you can see two bars, two stripes, titanium, aluminum, nickel, gold. You see, it is a 4-layer contact deposited by E-beam evaporation after
Excuse us, everyone. We are having a little technical difficulty, I guess, at the speaker's end. We'll get back to you soon, very soon. Please wait for a while.
Yeah. So this one. No? Okay. Okay. So there was some small interruption. So what actually I was describing in this slide is that on gallium nitride thin film, we have fabricated high quality nickel on GaN Schottky diodes. You can see the DC IV characteristics. So this is the reverse characteristic. This is the forward characteristic. So this is the semi-log plot. Means the y-axis is the log scale and the x-axis is the linear scale. So this linear region usually we fit, and by fitting this linear region, what we find out is about the ideality factor and the barrier height. Okay, so this linear region, when I fit, I get actually the intercept IS, and this is the relation between the phi b and the IS, and I can calculate the barrier height, the Schottky barrier height, which is, as I have told you, it's a very important parameter for a Schottky diode. In this case, we obtained 0.90. And now the slope of this line, is related to the ideality factor like this one. So once I measure experimentally or calculate the slope from this experimental IV graph, I can calculate the ideality factor, which in this case is 1.3. So this way we interpret about the quality and the properties of the barrier height or the Schottky barrier diode. I can tell, just seeing these numbers, I can see that this diode is not perfect. The current transport in this diode is primarily due to thermionic emission, but then there are other current transport mechanisms also which are there. So many things I can tell you. And another thing which I am not describing in detail, so this reverse characteristics is also very important, because for those diodes which are used for high power application, their breakdown voltage should be higher. So I just see this IV characteristic in the reverse, and I see that if it is going above some value, then the breakdown voltage is actually corresponding voltage will be called the breakdown voltage. So even breakdown voltage also we can measure from the IV characteristics. But for that, the system has to be a little bit different. You need to have, if your diode, you know, it is going to break down at a very high voltage, you have to accordingly, let us say, make a change in the voltage source. So this is finally, actually, I will stop here only, that the Schottky barrier diode, you can also do the CV measurements, and a Schottky diode is something like a parallel plate capacitor. So the capacitance per unit area is given by epsilon S by W, where W is here the thickness of the depletion region. And it is related actually to this equation. Square root of Q and D or E and D epsilon S VBI, where VBI is the built-in potential and V external is the extra voltage which we are applying. And now if I can rearrange this equation, 1 by C square and 2 VBI minus V external minus KT by E and D epsilon S, I can now actually plot a graph between. So you see 1 by C square. So this is an experimental graph for gold on gallium arsenide Schottky diode. So 1 by C square versus the bias voltage. So if we do that, we are going to get a linear curve. So you can see also 1 by C square is actually dependent upon the the bias, proportional. It's directly proportional to the bias. And the CV measurements are done in the reverse bias, not in the forward bias. So in the reverse bias, the capacitance is the depletion layer capacitance. So I'm interested only in measuring the depletion layer capacitance. So if the ND, if I want to, so this is slope actually. So this slope is nothing but d 1 by C square by dV external. So this is the slope of this graph. Its reciprocal is related to the dopant concentration or the carrier concentration. So I can calculate also the carrier concentration in a semiconductor material using the CV measurement. And also I can calculate the barrier height. So the intercept, if I see, I can calculate using this relation VBI plus Vn plus KT by Q, it gives me the barrier height. So even CV measurements also give you the barrier height of a Schottky barrier diode and also the carrier concentration in a particular semiconductor material. So this is another DC measurement which is very important for the characterization of the material as well as the Schottky barrier diode. So this is actually the, just briefly, this is the Keithley SCS4200 parameter analyzer. It can do both IV and CV measurements. And this is a kind of a dark box with a DC probe station. Micro probes are there, so we can probe very small contacts also. And we can do the measurements from, let us say, I think it is not 10 Kelvin at present, 80 Kelvin to higher temperature, 200 degrees Celsius. And so all those IVT, CVT measurements we can do using this setup. So this is, I think, I will not talk about MIS or MOS capacitor. So even we can do CV measurements on MOS. So this is all from my side. And I hope you could get some essential point about the DC electrical measurements on material, semiconductor material, as well as the devices. So thanks for listening to me. So if you have queries or questions.
Thank you, Professor Singh, for this meaningful and interesting talk. Now we have some questions from the participants. Raja Songdan asked if it is possible to measure resistivity of ferroelectric thin films by 4-probe method.
Yeah, so by actually 4-probe method is very versatile. You can measure the resistivity of any kind of sample. But as I have told you that you have to see what is the conductivity, or you have to know a little bit what is the resistivity of your sample. And the second thing is, accordingly, if its resistivity is very high, then you cannot use the setup exactly which you are using for semiconductor measurements. Okay. So they are actually what we call the low level DC measurements. So then you really have to go for those specific kind of instruments, and even your like a stage where you are loading the sample, that should also be electromagnetically shielded. So for high resistivity samples, usually there is a little bit trick to do the resistivity measurements. Hall effect obviously is not possible because there are no carriers, but even for resistivity measurement, you have to be very careful.
Yeah, there is another similar question from Nikita. She asked that does Hall voltage can be created with conductors and insulators too?
Yeah, with the conductors, it can be created. Yes, but it will be very small. You see, it is in, if I take, you see, this is a very important question, and it's important to know this thing, that Hall voltage VH is inversely proportional to the carrier concentration. Okay, so obviously, if carrier concentration is something like in a semiconductor where I am in the sort of range between metals and insulators. So there I get a voltage value which is easy to measure. Something like 1 volt, 100 millivolt, 10 millivolt, or maybe 10 volts sometimes. So these voltages are little easier to measure accurately with our let us say digital multimeters or voltmeters. But if you have a metal, you see, the carrier concentration in a metal is 10 to the power 23. In a semiconductor, suppose it is 10 to the power 17. So there is a 6 orders of magnitude difference in carrier concentration. Obviously, there will be a 6 order of magnitude decrease in the Hall voltage also, if the geometry is the same. So that if I am having 1 volt, then it will be 1 microvolt. To measure 1 microvolt, it is quite tricky actually. So that's why we have to do something in the setup. So to do measurements on very, very sensitive samples in the sense that the voltages which we are getting are very small. In the insulators, you cannot get the Hall because you see it's very, very difficult to do even ohmic contact fabrication on the these insulators, and there are no carriers basically in insulators. So there is no current, DC current flow is not there. So you cannot do the Hall measurement.
And there is one question from Prakash Yadav that what is the reason behind it? We measure Hall voltage perpendicular to source voltage.
We measure, yeah. So I think that was already shown there. You see, in Hall effect, what you are doing is you are sending, suppose the current is flowing in X direction, and in the Z direction, you are applying the magnetic field. Then due to the Lorentz force, the electrons or the holes will be deflected in the third direction. That is the Y direction. Okay, so due to their deflection, there will be a voltage which will be developed along this third direction. So this voltage, this electric field will try to, so since there is an electric field, there will be an electric force. So this electric force and the Lorentz force will balance each other after a particular time. So this Hall voltage is always developed because there is a vector product V cross B. Okay, so it has to be V is the direction, V is the drift velocity which is in the direction of the current, B is the magnetic field direction, V cross B, the cross product definitely has to be in the third direction. So that's why Hall voltage is in the third direction.
Jyoti Mishra asked, in what way is the planar Hall effect induced by the chiral anomaly in Weyl semimetals?
Okay, so I cannot actually hear you. Maybe again you can repeat it.
Yeah, sure. In what way is the planar Hall effect induced by the chiral anomaly in Weyl semimetals?
In which metals?
In Weyl semimetals.
Okay. So you see, uh, uh, what I talked about is the simple Hall measurement. Okay, the simple DC Hall measurement, and we have different kinds of Hall effect nowadays, depending upon what kind of material you have. As she has given an example also, or some semi-metals or Weyl semi-metals and so on.
Yeah.
So what you see is you also see other quantum mechanical effects, and you see anomalous Hall effect. You see some kind of this thing. If you take at very low temperature and high magnetic field, you also observe. In semiconductors, you can also observe a quantum Hall effect. Okay, but for doing those kind of measurements, and what is actually like the physics of quantum Hall effect or anomalous Hall effect, that's different from what we study for the classical Hall effect. So what I have described is the classical Hall effect. So to describe a quantum Hall effect or anomalous Hall effect, or there are different nonlinear Hall effect also nowadays is there. There's a recent paper actually in which you don't need a magnetic field. Without magnetic field also, and it is a planar very thin sheet of a 2D material, and it is in semicircular stripe shape, and it is called the nonlinear Hall effect. There also you can see the Hall effect. So you see, those are some special kind of versions of the Hall effect.
There are a few questions from Bhanupriya. So first one is, which is the best method we can use to have the best electrical properties of the oxide thin films?
Oxide thin films.
Yes.
You see, as I have described you, we also work on different types of oxide materials. So if your oxide material is a semiconducting oxide, then you can use the usual techniques which we use for normal semiconductors, like resistivity, 4-probe resistivity, or van der Waals for probe resistivity is very simple to do in any lab. You just need to have a digital multimeter and a current source, a good quality current source, and then the Hall effect measurement. So using these things, you can measure on oxide materials also if their conductivity is in the semiconducting regime. Plus, you have to keep in mind that you need to fabricate a very good quality ohmic contact in order to have very reliable measurement. You see, you may be having 50% error, but if you want to be only within 5% error, then you have to keep in mind that you have to fabricate very good quality ohmic contacts also. But if it is an insulating oxide, then as I have replied earlier also, you have to develop a special type of setup actually, and properly electromagnetically shielded, and you need to have very, very sensitive instruments so that you can measure it properly.
And she also want to know that, can we calculate electrical properties of the thin films grown by using some chemical process? Kindly tell two physical and chemical methods we can use for calculating electrical properties.
So calculating the the electrical property using chemical method.
She means she grown, I think question is that she grown thin films using some chemical process.
Yeah. For those thin films can be done. Not a problem. You just, as I showed you in the beginning slide, you just need to have a thin film on an insulating substrate. That you have to keep in mind. This thin film, if you are depositing on a semiconducting silicon substrate, then you cannot get demarcate actually between the electrical property of the film or where it is coming. There will be some weighted contribution coming from the substrate as well as the thin film. If you are depositing thin film, even by chemical method, you deposit it over a insulating substrate and then do the resistivity and Hall effect measurements. You can do that.
And another question from Kapil Nayak. So he is asking, when we are going to measure the resistance using 4 probe or whole measurement of thin film, what will be the effect of substrate?
Yeah, that's what I told just now. The substrate, to remove the substrate effect, you have to use an insulating substrate. You use the insulating substrate, you will not see the effect coming from the substrate. Only the, because mostly what we are doing is when we are depositing a thin film, I already know about the substrate. I am just interested to know about the property of the thin film which I have deposited. So it's better to take an insulating substrate like sapphire. You can deposit over sapphire. You can deposit over a good quality glass substrate or semi-insulating silicon.
Rajesh Kumar Sukla want to know that how to measure resistivity with a low cost apparatus or homemade without using Keithley apparatus.
Yeah. So you see, as I have told you, the van der Pol method is the simplest in that sense. There is no restriction from the what kind of geometry of the sample should be there and what kind of geometry of the 4 contact should be there. So that is actually the best method to do like let us say low cost electrical measurements. And apart from that, you see, in any measurement, when you are calculating resistance is equal to V by I. So what you have to keep in mind is the final error in the calculation of resistance will depend upon how much is the error in V and I, because errors always add. If you have 5% error in V measurement and 5% plus minus in current, which is flowing through the sample, then 10% error will be there in the resistance measurement. So that's why I told you that when you do with the Keithley, the high quality or very sensitive Keithley instruments, we actually get very accurate values of the resistance and the resistivity. That is the only aim. If you are having a low cost equipment in your lab, you still can do the measurement. The thing you have to keep in mind, the error in the final measurement will be higher.
Dr. A.L. Saroj want to know, please explore the microwave irradiation on bipolymer electrolyte film regarding conduction path through the matrix and mechanical strength of the film.
Yeah, so what she wants to know?
Microwave irradiation on bipolymer electrolyte film regarding how is the conduction path. Yes.
So no, I could not get the point. Like what is the question?
Actually, question is not directly related with the talk, but we want to know that effect of that microwave irradiation on the bipolymer electrolyte films. So regarding conduction path through the matrix and mechanical strength of the film. So how it will affect that one?
Okay.
Yeah.
Yeah. So you see, in this case, you have to do a vertical like measurement. It will not be something like, let us say, you have to have what another thing can be done is that you take a substrate because I am not working in this polymer films and like this one. So what if the polymer film is self-standing? So you can take a top and bottom geometry. You take one top contact and one at the bottom, and then study the vertical current transport. So in that way, you will be, I think, able to see the effect of these conduction paths in the polymer film.
And one more question is from Hiren. So he want to ask that how to make 7 nanometer semiconductor.
What is how to make 7
nanometer semiconductor? Which technique used for made nano semiconductor?
Yeah, nano semiconductor you can make by various methods. There are top down approach also and bottom up approach also. So if you want to make a 7 nanometer, suppose nanowire of some semiconductor, you can use nanolithography technique like electron beam lithography. And by that you can just do the fabrication of a nanowire. And if you want to use the bottom up, you can do the chemical vapor deposition, the famous method which you have, BLS mechanism. So although the control will not be that much high, it will be 7 nanometer plus minus something, but you can do that. The bottom up approach, and the top down you can do more precisely. Okay, if you want to create 7 nanometer semiconductor nanowires, that is possible, but that is actually reaching the limits of even e-beam lithography also.
And he also asked to give just knowledge of processor which made by semiconductor.
Processes, okay.
Processor which made by semiconductor.
Silicon. No, he wants to ask the details about this thing.
He just asked the knowledge of processor which made by semiconductor. Yeah, he want to know.
Yeah, it is made by silicon. You see, I could not come to that discussion. So the processors are made out of silicon nowadays. But this is like, let us say, the device is a field effect transistor device where you have a source, you have a drain, and then you have a gate and the gate dielectric. So I was about to come to that one, but that needs actually more elaboration and another lecture. So you can do IV measurements on those things also, on those devices. People do that. That's quite regularly they do, who do research in this area. So they measure actually the IV characteristics. So since it is a 3-terminal device, you have an output characteristics, you have a transfer characteristics. So drain current as a function of drain source voltage at different values of the gate source voltage. So this is called the output characteristics. And then you can do the transfer measurements. So these are the DC measurements and plus the CV measurements, which I today could not discuss due to the lack of time. So CV measurements, you can calculate the threshold voltage of the transistor. You can calculate the traps inside the oxide or at the interface. And using the transfer characteristic DC measurements, you can calculate the mobility of the carriers. So a lot of information you can get from the DC electrical measurements, even in these microprocessor transistors also.
And so there are 3 questions more. One from the Harika Chaurasia. She wants to know that it is possible to convert an indirect band gap semiconductor into a direct band gap semiconductor via doping.
No, via doping, it's not done. Yeah. You see, the nature of the band gap of a particular semiconductor is its inherent property. Okay, so suppose silicon, the normal silicon, it is indirect band gap semiconductor, it will remain indirect. So by doping, you cannot change its band gap, nature of band gap. You can change the amount of band gap. If you do the doping, the band gap can decrease actually. Okay. Or in some cases like zinc oxide, it can increase by doping. If the doping has to be very high actually, there are some Burst-Mostein effect is there, due to that the band gap can increase. But you cannot change the nature of the band gap.
There is a related question with Ankit Kargeti. He wants to that how do we determine whether our sample is having direct band gap or indirect band gap?
Okay, so that very simple measurement you can do is photoluminescence. Okay, in the photoluminescence, the PL technique, what you do is you shine a laser light on the semiconductor, and the luminescence, the light which comes out of the semiconductor, you collect that and you analyze that and you make a spectrum between the intensity of the light which is coming out and the wavelength. So wherever you will see a peak, one main peak you will see, it is corresponding to the band gap of the semiconductor if it is a direct band gap semiconductor. There can be a defect emission peak also, but that you can distinguish very easily. This peak is very sharp. So in an indirect band gap semiconductor, you don't see that PL emission peak, what we call the band edge emission peak. You don't see in indirect because the emission efficiency is very low. You see it only in the direct band gap semiconductor. So using photoluminescence measurement, it's a very good technique to tell whether it is an indirect or it is a direct band gap semiconductor.
The similar question was Shivanshi Tiwari, and I think you have answered that. Why photoluminescence can't be done with silicon?
Yeah, that's what I told already. It is an indirect band gap semiconductor.
And Dheeraj Kumar wants to know that which temperature we are considering the room temperature.
300 Kelvin. 300 Kelvin. Typically, we take 300 Kelvin as the room temperature. Hello?
Yes, sir. And there is one more question by Vipin Sharma. How we calculate the band gap by photo emission spectroscopy technique? I think it is also same.
Photo emission is a different technique, actually XPS. I think he means to say X-ray
Yeah.
photoelectron spectroscopy. So there are actually this more elaborated method to calculate. So it doesn't, you see, there is a photo emission is a much more evolved method and more sophisticated. And with that, you don't only know about the band gap of the semiconductor, which is actually one parameter, but you also can see the type, the valence band structure, the conduction band structure. So if you know the conduction band structure, the valence band means the electronic band structure, EK diagram. So the band gap naturally comes out of that one. Once you know the EK band structure of a semiconductor, obviously you can get the band gap.
And one more question from Mohit Sani is that which measurement IV or CV give better values of barrier height and why?
You see, it's a good question. So IV measurements give you a barrier height value, and in that we have to keep some things in mind depending upon the dopant concentrations. There is a Schottky barrier height lowering effect also. So this barrier height usually what we call is the apparent barrier height, what we measure by the IV measurements. And then by the CV measurements, we measure a barrier height which is more close to the actual barrier height of a metal semiconductor contact. And then there is a relation actually between the barrier height measured by the CV method and by the IV method. But for that, what you have to do is you have to do, maybe some of our students' papers are there in this area. So temperature dependent IV and CV measurements have to be done. And then what we call is the barrier inhomogeneity model. So this barrier inhomogeneity model says is that at the metal semiconductor interface, there are nanoscale regions of Schottky barrier heights having higher and lower barrier heights. So if I do temperature dependent IV measurements and CV measurements, I can get the experimental value of the CV, the barrier height by CV, and correlate or relate it mathematically to the barrier height which I have measured from the IV method. But there's like, I will not say there's a better method or something, but CV gives you a little bit different value than the IV measurement.
And I think now we have the last question from Rupali Deheria. So where we use TLM?
TLM
Yes.
actually in this context we use for the calculation of the specific contact resistance and the contact resistance.
And what will be the best topic for research in this field?
Oh. That is a very relative question. So the semiconductor area is devices area, and this is very wide. But I can tell actually like two very important areas and hot topics are, one is the 2D materials, the 2D semiconductors. Because in these materials, the knowledge what you have learned in conventional semiconductors like silicon, germanium, gallium arsenide, many of the things are different there, even from the material device point of view. So many unknowns are there in the 2D semiconductors. So if from that point of view, I see 2D semiconductors is a very interesting, and many unknown things are there. But from practical device application point of view, you don't have practical devices which are used in market or commercial production. From practical point of view, the three wide band gap semiconductors like gallium nitride, which are used for light emitting diodes, white LED applications, high electron mobility transistors. So these materials have a direct application. Many of the things are there already known. So from research point of view, you find very difficult to have a good research problem there. But it has direct application. You see, you use LED in your everyday application. You use in mobiles the transistors based on gallium nitride. So you see, it depends upon you what interests you more. The unknowns, but not many application, or many knowns, but lot of applications.
I guess that's all, Dr. Sandeep, from your side. So I would like to go ahead and let me once again thank Professor Rajendra Singh for his wonderfully managed and very, very informative, highly informative talk on this topic of electrical characterizations. I'm sure our participants have been benefited very much. So thank you very, very much, sir. And yeah.
Okay.
Yeah.
Thank you,
So,
Yashpal.
yes, sir.
And thanks to all the participants.
Yes, sure, sir. So it's for the participants. We have another technical talk today at 2 o'clock. So you may join us at the same Zoom link for that talk. So thank you very much, everyone. We are ending here. So thank you, sir. Thank you, sir. Bye-bye. Yeah.